here's the concluding examples that are included here in this 7.2 section, or 7.1 section, sorry. As we look at this next one, it talks about the angle of depression from the top of the building to a point on the ground is 32 degrees 30 minutes. So here's our building, and the angle of depression would be off of the horizontal line, and it would be going down, and they're saying it's 32 degrees 30 minutes. So they're back to using degrees and minutes. And we come here, and here's the ground. And let me get rid of that extra stuff. Okay, so there's my picture. They would like to know how far is the point on the ground from the top of the building. Okay, so they would like to know how far is the angle of depression from the top of the building to a point on the ground. How far is the point on the ground? So we'll say this point right here from the top of the building. Okay, so they're looking for this side length right here. Well, okay, and we know that this is 252. So we're given a side, and what? This isn't even from this section. This is back in chapter 2. We got a right triangle, which is going to be easy. Okay, so let's figure out what this angle is right here. It's got to be the makeup to 90 degrees. So 90 minus 32 degrees 30 minutes is going to be, well, that's going to be 89 degrees. I'll do it one more time here. 89 degrees, sorry, 60 minutes minus 32 degrees 30 minutes is going to be 57 degrees 30 minutes. So this is 57 degrees 30 minutes. So what do you know? You know that the cosine of 57 degrees 30 minutes is equal to adjacent 252 over hypotenuse. We're going to use the cosine coming through there. And that's because we want that hypotenuse length, and we're given the adjacent side. So I hesitated to just know what they wanted. It makes sense that they want to know the distance from the top to the bottom, as opposed to the straight across distance. We could have got that without any trig. We just walk a measurement tape out there, but it would be hard to run the measurement tape from the top of the building down to the point, and I don't have to. So x then would be equal to the 252 divided by the cosine of 57 degrees 30 minutes. So let's do that. Let's take the 252 and divide by the cosine of 57 plus 30 divided by 60, right, which you know is 0.5. And we get a straight value there of 469, and it was meters. 469.01, so we'll do 469 meters. So not bad at all, right? So they're keeping us honest by throwing in a right triangle, making sure we're not going to go crazy and use the law of sines when we don't need to. So now we got a big description of a problem about two docks. So two docks are located on an east-west line, 2,587 feet apart. So let's let this be dock A and dock B, and I'll put points on them, and they are straight across 2,587 feet apart from one another. From dock A, the bearing of the coral reef is 58 degrees 22 minutes. Okay, so a bearing is off of the straight north-south line, 52 degrees 22 minutes, and we're looking like that for a coral reef. From dock B, the bearing of the coral reef is 328 degrees 22 minutes. So again, off of the north-south line, we're going to go 328 degrees 22 minutes, and we're going to go up like this, and we'll just look at the intersection of those two lines, okay, and say that they intersect out here. So here's the reef. The reef's way out there. Okay, and we've got dock A and dock B. So let's figure out some things. Now, we could go through a lot of arguments to go through and find out what this is. But this guy right here is going to be got um, well, actually, let's go through and do this. So this is, I apologize, I wrote this wrong. 58 degrees 22 minutes right here. So we got that one right there. So we need to figure out what this angle is right here. Well, actually, what do we even ask to find? Find the distance from dock A to the coral reef. We'd like to know this distance right here, which I'll call little b. Okay, so if we want to know little b, I'm going to need to know the angle opposite it, and I'm also going to need to know the angle opposite the given side. So if we look, we can figure out what we have. So what do we have in here? If we come here, we have a 90-degree angle, and we are going to need to take off the 58 degrees 22 minutes. So I got a 90-degree angle, and I'm going to need to take off the 58 degrees 22 minutes in order to find this angle A right here. Okay, so that's angle A. So that's 89, 60, and so if I look at what that is, so if I look at 60 minus 22, I come up with 38 minutes. And if I look at 89, plug that in, right, minus 58, I end up with 31 degrees. So I have 31 degrees, 38 minutes right here. And then what do I have here? If I look at the 328 degrees, if I go all the way around, it's 360. So if I look at 360, which I'll write as 359 degrees, 60 minutes, and subtract away the 328, 22 minutes, I end up with 31 degrees, 38 minutes for right here. So that's interesting, right? That's what's coming out for that angle right there, is that we get 31 degrees 38 minutes. But is that right? So sometimes we mislabel things. I just want to model that. Where is this 31 degrees 38 minutes? It's actually right here. 31 degrees 38 minutes isn't where I put it. It's the makeup to that line. So thinking about that, we already know our answer for this. Oops, forgot that I had the pixel eraser going on. So let me draw those lines back in. That's where the 31 degrees 38 minutes is. So what's this angle right here? Oddly enough, it's 58 degrees 22 minutes, or maybe that isn't odd to you. But that angle right there is 58 degrees 22. Now, how did I get that so quickly? I knew that 58, 22, and 38, 138 added up to 90, and that's what this angle is right there. So you're going to do some thinking work. Got to switch back to the object eraser to help myself out there in the future. So remember what we found. This was 31 degrees 38 minutes, and we could have gotten that through other lines, but angle B there is that. And then what do I have? I have two angles and a side. So now what do I have to do? Well, keep doing the same things. Now I got to take the 58 degrees 22 minutes. Add to that the 31 degrees 38 minutes to come up with 22. And look what happens here. Here we get a 60 minutes. Here we get 89. And so here's what we find out. That this is a 90-degree angle up here. So the angle that these happen to meet at is a 90-degree angle. So we did all of that work, and now we don't have to do as much. We don't have to use the law of sines, although we can. What do we know? Let me show it both ways. So we did all of that work. I couldn't justify that was 90 until I did all that work. But take a look at what we could do. We need to know side B. They want us to know the distance from the distance from dock A to the coral reef. So they want to know that side length B. Well, I could do something like this, that sine of 58 degrees 22 minutes is equal to opposite over hypotenuse. That would work. Okay. The other thing that I could do is say 2587 over sine of 90 degrees is equal to, right? So that side length is equal to the sine, b over the sine of 58 degrees 22 minutes. Right? That would also be the same. Now, they are essentially the same. Remember what sine of 90 degrees is. It's 1. Right? So this would be 2587 is equal to b over sine of 58 degrees 22 minutes. That's the exact same thing as this. It doesn't look the same, but if I manipulated and got the sine up and look, if I solve for b in both cases, what's b going to be? It's going to be the sine times this. What's b going to be? The sine times the 2587. So b is the sine of 58 degrees 22 minutes times 2587. So let's find out what that is. Sine of 58 plus 22 divided by 60 times 2587 is equal to a length of 2202. It's 2202.6, so we'll do 2203. And everything was in feet. Now we know our distance from coral reef to A. Okay, so then we got this nice picture here of a triangle here. They have this at least a couple times in the homework. And it says 3 atoms with atomic radii of 2.0, 3.0, and 4.5 are arranged in the figure. Find the distance between the centers of atoms A and C. So they want to know that distance AC. So let me take a moment just to redraw this thing over to the side. So here's A, they have down here. Here's C, and here's B. So what do we know? We know that this is 18 degrees. They gave us that, and this guy. And we know that the distance from C to B is, well, it's talking about how the radii is 2.0. So it's 2.0 from the center of the green circle to the edge, and it's 3.0 from the center of B out to its edge. So this is a total of 5. So apologize if you're not seeing what I'm writing. Let me highlight it. It's 2.0 from here to here. And it's 3.0 from the edge of the pink into the center for a total of 5. By the same argument, knowing that this is 3.0 right here from pink to the edge, and this is 4.5, this distance here from A to B is 7.5. And the question that they want us to know is, what's the side length B, right? What's the length from A to C is how I'm reading that. And we got 2 sides and a non-included angle. Well, that's great. We need to know, and that's all they want, is to find the center between the distance between those two. And so what do we know? Well, we're going to have a little bit of a problem, because if I go to set this up, I was told I could do that. If I were to set this up, I would say, okay, 5 over the sine of 18 degrees is equal to, B, what I want, but I don't know what B is. I don't know what the sine of B is, so I'm going to have to do some work. This is the first time that we didn't have 2 angles given to us, and we got to see what that's like. Well, if we don't have 2 angles given to us, then I got to go start to solve for the triangle, these other angles. And so what we're going to say is that sine, go back here to the pen, sine of 18 degrees over the 5 is equal to the sine of C. Now, why they pick C over B? Because I know C's opposite side. And that's going to allow me to get what C is. So I now know sine C is equal to 7.5 times sine of 18 degrees all over 5. So if I plug that in, if I take 7.5 times sine of 18 divided by 5, I get a number. So I get sine C is equal to 0.46352 dot dot dot. I'm not going to round that off. I'm going to go and take on my calculator sine inverse of that. So sine inverse. So C is equal to sine inverse. And then I'm going to bring up the last answer, right? Or this 0.462 guy. So bring up that last answer, and I'm going to get C is equal to 27.6 degrees. 27.61, but I'll do 27.6. So awesome. Well, how does that help me? It helps me because now I can figure out what B is. So we know what B is. B is going to be equal to 180 minus the 18 minus the 27.6. So if I look at 180 minus the 18 minus the 27.6, I get a B angle of 134.4 degrees. Okay, so now what do? I come in here and say I'm set. I was always looking for little b, but I didn't know the angle opposite it. So I had to go work for that. And then I can come right back to my 5 over sine 18. It's where I wanted to start, but I realized I had a problem. So what's b equal to? Well, you know, it's like all the other ones. So we're given lots of examples here, mainly to show the similarity between each one of these. Remember to shut off your what sign's working on and all of that. So I'm getting B equal in 11.56. So B is equal to 11.6, or maybe they wrote 12. It doesn't truly matter as long as you're coming up with an answer like that. I would look at your work and give you full credit. So in these last couple of examples, actually just this last one, I'm going to skip 9. 9 is actually that example 9. It's not really an important problem for us. It's pretty detailed out. I would never give something like that on the exam, so I'll check the homework as well. But they want us to verify that the area of the triangle using either the 1/2 base times height or the 1/2 a sine 1/2 a b sine c gives the same result in this triangle. And so let's take a look at it. Let's use the area is equal to the 1/2 the base times the height formula. So the area would be equal to 1/2 times 2, and the height is root 3, and so the area would be equal to root 3 using that formula. If we use the other formula, a is equal to 1/2 a, which is 2, b, which is also 2, and sine c would be the sine of 60 degrees. So a here would be equal to 2, right? The 1/2 and the 2 would cancel to be 1. Sine 60. We know that sine 60 is root 3 over 2. The 2's cancel, so no matter which way we do it, we get a being root 3. Again, that's our last example here from 7.1. Let's skip this other one because it's a little bit crazy, and we'll prepare ourselves to get into 7.3. We're going to initially skip 7.2 and go right to 7.3 and learn the law of cosines, and then come back to the ambiguous case of the law of sines. It will help us understand it better.